nanoHUB-U, online instruction.
Hey everyone. Last lecture we were actually talking about how to construct S-matrix formulation, and now we're actually going to try to extend it to include periodicity. And so it's a reasonable question to ask, what if one or more of the layers in our S-matrix had some lateral periodicity? Okay, so you can think of like two types of coupling, really. One would be like if we have basically periodicity in the z direction, like the direction of propagation, but then there could also be diffractive coupling, which would be basically if you have modes in the parallel direction to propagation that have different k vectors. And then the question that we have to ask ourselves is, can we create a single framework that could capture both types of effects, especially with the S-matrix formulation? So just to recap briefly what we talked about last time, remember that we actually calculated that there's this S tilde matrix that connects like your pair of layers, like outgoing beams as a function of the incoming beams in a pair of layers, which is given by S tilde, and that's the interface matrix S, which is constructed from the T matrix, times these phase factors here. And then in order to come up with a transverse periodic solution, then we have to extend that in the following way. So first we have to divide the whole structure into uniform layers in the z direction. Okay, so if we do have periodicity, we have to basically define a layer that has essentially uniform periodicity across that z value, right? And it could be multiple layers which have different periodicity. That could be okay. But then we have to find the block states in each of those layers and then calculate a transfer function for the field amplitudes within this layer as well as across layers. And then that allows us to iteratively develop the S-matrix. Once we have that S-matrix, including periodicity, then we could actually pick inputs and then get physical outputs for transmission, reflection, and absorption of the system. And there have been at least a couple of papers that have tried to do this, first being Whitaker and Culshaw in Physical Review B, and so that was published in 1999. And then there's a related effort by Tikadev et al. In 2002. Basically going into more detail about the periodic solution strategy that was used in both these papers, the basic concept was to take the H field and then do a Fourier expansion in the different wave vectors in the lateral direction represented by the kx plus these reciprocal lattice vectors gx and gy. And so this is basically an expansion that's written in this form. And you can see that there are these coefficients, phi x and phi y, that are very important, that represent the coefficients in each direction as a function of the reciprocal lattice vector g. And so you can actually simplify or kind of combine these expressions into more compact representation momentum space that looks kind of like this. So you have basically a phase factor associated with the wave vector in the z direction, which we previously called beta, now we're calling q, times this phi x, x hat, phi y, y hat, and then we subtract this z component correction, which goes as 1 over q. And then once we have this H field, we can use Maxwell's equations to calculate the E field, and then the E field looks something like this. Obviously has the same e to the iq z, but there's a 1 over q dependence, and then there's like a cross term with ky and kx hat directions, and then similarly like in the phi y component as well. And then once we have that written down, we can actually write down an eigenvalue equation in which we kind of extract the phi's that were the coefficients in the E and H field, and then we create an eigenmode equation in terms of the phi x and phi y terms, rather than trying to explicitly write in terms of the E and H fields. And the reason we do that is it allows us to create a fairly compact representation of what happens as you propagate within the layer. And so basically you can see here that we have something that's just written as a standard eigenvalue equation for phi. And you can see that this left-hand side and right-hand side, it has some comparison or analog to the earlier master equation that we had in Unit 1 on band structures, okay? But this is slightly different. And the eigenvectors phi, the phi x and phi y, have kind of an unusual orthonormality condition. So it's not just that phi n transverse times phi n prime would be equal to a Kronecker delta function, but you have to put this matrix omega squared minus script k in between them in order to enforce orthonormality. So that occasionally causes problems. Fortunately, there is another trick, which is to actually write this as a generalized eigenproblem, and then you can use a simpler orthonormality condition. So neither is necessarily like computationally really easy, but it's definitely doable. And in the next lecture, we'll talk in more detail about how that works.